Okay, so welcome back. In the previous class, we started discussing about singular value decomposition and its foundation stone, what it is about, why it is useful, where it is useful, and what are the preconditions of using singular value decomposition. So it turns out orthogonality plays a central role in you being able to decompose a matrix into a singular form, right? And typically these are rectangular matrices, right? Which is what is more likely, I mean, in real world applications, right? So there is this one property that we discussed, that orthogonal transformations or matrices are angle preserving as well as length preserving, okay? We also discussed that eigenvalues of a symmetric positive definite matrix, which you will see that one of the matrices on the right hand side, when you use the singular value decomposition, turns out to be a symmetric positive definite matrix. So it turns out that the eigenvalues of the symmetric positive definite matrices are positive, which is really, really important for us because the singular values are nothing but the square root of the eigenvalues. So the eigenvalues needs to be positive so that the singular values also turn out to be positive. And we can arrange these singular values in a descending order. And based on the magnitude of each of the singular values, the importance of information across that direction or that dimension, it turns out to be stronger or weaker. Okay, all right. And so, I mean, while explaining singular value decomposition, we came across this symmetric positive definiteness, which is nothing but whether you try to figure out, given a quadratic form, a quadratic expression, you try to figure out whether that quadratic expression stays positive. Okay. All right, so we invoke parabolas, right? I mean, because that's the geometry that easily comes to our mind. And so what we wanted to actually show is that the left-hand side, which is this, right? I mean, this left-hand side is this guy. We wanted this guy to be positive, okay? And so we just use some basic high school algebra and wrote it down to this kind of a form. And there we have seen that there is a perfect square. This could be greater than or equal to 0, right? And so therefore, and since there is a y square which is by default positive and a square which is also by default positive, so everything boils down to the sign of ac minus b square, which also turns out to be the determinant of this particular matrix. Okay, so what happens is, if this is positive, then this expression stays positive. So a positive definiteness of a quadratic form depends on whether AC minus B square, the determinant of the matrix under consideration, is actually non-zero. That is very, very important. So that's non-zero, okay, which means the matrix has a full rank. Okay, so such matrices, it turns out, if the matrix is a symmetric positive definite matrix, which means if their eigenvalues are all positive, then this guarantees that this particular quadratic form stays positive under the assumption that its leading coefficient A is also positive. And that helps us figure out whether such quadratic forms have a local minima or not. So it's a direct connotation to an optimization problem. Okay, all right. So even though we are talking about singular value decomposition, I thought we should bring this up because the geometry, as a matter of fact, is very, very interesting. Okay, so let's clear the canvas. So what we wanted to say is the following, that if your matrix A is SPD, right, there is a direct significance in convex optimization problems. And in machine learning, you actually end up solving such problems quite a lot, which means SPD means the eigenvalues are all greater than 0. So if a matrix has eigenvalues all greater than 0 and the matrix is also symmetric, then I can say that the corresponding quadratic form, the QF, which we can write in this manner, X transpose AX, will be strictly positive. And such quadratic forms will have a local minimum. Okay, basically an example of a parabola facing up. Okay, I mean, I brought this up not in the context of singular value decomposition, but I just wanted you to show that how the geometry of certain things, of certain optimization problems in higher dimensions can be represented using the concepts that you have learned. Okay, so now the back to SVD. Okay, so this was just a side note, but nonetheless a very, very important one. So we are back to singular value decompositions now. And just so we recall that we are dealing with a non-square, a rectangular matrix, okay? And what we want to do is to break this up into 3 pieces, okay? All right, and this is M by N, which is a rectangular matrix, okay? And so this is nothing but M by R. This should be R by R, and this should be V is N by R. Okay, all right. Now each one of these U and V, each one of these U and V's are orthogonal matrices. Okay, it's a nice property. So such, if you are able to break our matrix under consideration into these 3 pieces, then we can say that, you know, I can compute the singular values. But having said that, computing singular values directly from this form is not easy. In fact, it's very difficult to see how you are going to compute the singular values because your matrix is a rectangular matrix, right? Okay. So in order to understand how eigenvalues are computed and what's the relation between eigenvalues and singular values, let's just look at this. Okay, so we know this, right, from previous discussions, that if your matrix is a square matrix, right, you can decompose your matrix into this form. Okay, all right. And here what we are looking at is this. So obviously these 2 forms look very different from each other, right? I mean, now when I look at this kind of decomposition, your matrix P doesn't have to be orthogonal. Okay, all right. I mean, it could be just linearly independent columns, and that should suffice for the inverse of the matrix to exist. However, if P turns out to be orthogonal, then you can rewrite this as PD P transpose, right? Okay, all right. I mean, even then, even though now we got rid of the inverse and we replaced the inverse with the transpose, this kind of, there is some sort of a structural similarity, right? But still, I mean, these 2 are not same. Okay, so what happens is here we actually can compute the eigenvalues. Here we compute the singular values. Okay, but the question is, how do we deal with a rectangular matrix? Okay, so one other thing that you need to understand is that this particular matrix or linear transformation contains the basis vectors, and these basis vectors are along the columns of this matrix P, and the basis vectors of this guy lies along the columns of U and then along the columns of V, right? And these basis vectors themselves are very, very different from each other. Okay, all right. Okay, so now how do I deal with this? So this is the reason I say that transposes are so nice, is that now let's look at, since I cannot handle a rectangular matrix in this particular form, what I can do is I can look at the product of the matrix A with its transpose. Okay, all right. So, sorry, I mean, I think I should not have written it here. So let me erase this. I'll rather write it on this portion. Okay, all right. So what I want to do is that I want to look at the transpose of this A, okay, not that A, all right. Well, let's see what we get. So for clarity, let's call this, right? And then we have U. Okay, so I'm sure we can open this up, right? So the first expression on the right-hand side. So if we open this up, it is nothing but V transpose, right? Which is nothing but V, right? And then this singular matrix transpose, right? And then U transpose. Okay. And then what we have from here is nothing but an U, a sigma, and a V transpose. Clear, guys? Okay. Now, the thing is, what do we know about U and V? We said that, you know, in a typical singular value decomposition, this U and V have to be orthogonal. Okay. Whereas in a typical eigenvalue decomposition, P doesn't have to be orthogonal. But here, that's a kind must, right? So if U is orthogonal, then this guy is nothing but the identity matrix, right? So what we have is this V So let's wrap the parenthesis around this in the middle guy. Okay, all right. Now, guys, look carefully. Okay, now what we have, if we go back to the eigen decomposition of the matrix, right? This is, I mean, on the left hand side and on either side of the diagonal matrix, you have the same matrix, right? P, D, P inverse. On one side, you have the transpose of the matrix. So now let's come back here. And that was not the case here, right? When we initially wrote the decomposition, but if you take the transpose, right, from either direction, okay, what we now have is that we have the same matrix on either side of this middle guy. Okay, so now we have more structural similarity compared to the eigen decomposition of the matrix A. Okay, so we are still talking about the singular value decomposition, and what is of particular interest is this guy. Okay, now no matter what, I mean, no matter what your sigma is, whether it's a real symmetric matrix or not, when you look at sigma transpose sigma, so any matrix A transpose A has to be symmetric by default. Okay, all right, and that is something that we have observed in PCA as well. So this guy is definitely real and also symmetric. Okay, all right. So, and this also turns out to be a diagonal matrix that we will see. Okay, all right. Now, if you do that on the right hand side, I mean, if I can do it on the other side as well, right? If you do that on the right hand side, which is AA transpose, I'm not going to repeat the calculations. What you should end up getting is this U. Okay, all right. So now if we compare this guy with these guys, then what I can say is that this diagonal matrix D contains the eigenvalues of A, and this matrix P contains the eigenvectors of A. However, what can we say from here is that this diagonal matrix contains not the eigenvalues of AA transpose, it contains the singular values of AA transpose. Okay, so this guy contains the singular values of AA transpose. But now, by virtue of such transformation, this guy U contains the eigenvectors of AA transpose. Okay, all right. So this guy U contains the eigenvectors of AA transpose. Similarly, if you come here, you can say that V contains the eigenvectors of A transpose A. Okay, all right. So this is how we establish the similarity, because we have to somehow be able to compute the eigenvalues, right? Now, in a singular value decomposition, since we are not able to compute the eigenvalues, we have to be able to compute the eigenvalues of A. We have to be able to compute the eigenvalues of some matrix, and that some matrix is given to us by this A transpose A or AA transpose. Okay, so the principal difference between the two is, once again, A is a real matrix, real and symmetric matrix, and a square matrix, and it is decomposed in this fashion, where you have a diagonal matrix which contains the eigenvalues of A, and the columns of P is nothing but the eigenvectors of A. However, in a singular value decomposition case, the columns of U contains the eigenvectors of AA transpose, and the diagonal matrix of the singular matrix contains the singular values of AA transpose, or in other words, since we know that AA transpose is A square, if A is orthogonal, this contains the eigenvalues of A square. Okay, so since we cannot compute the eigenvalue of A directly, we use the transpose operation and we compute the eigenvalues of A square and take the square root, and that gives us the singular values of A. Okay, so in other words, if I have to establish a relation now, it is you compute the singular values of A. This is what you want to compute, A SVD, sorry, and this is nothing but the eigenvalues of A transpose A. This is very, very important. Okay, so this is how you actually compute the singular values. Okay, so you take any example, right? I mean, so what is happening is the following, that I can break this up. Now let's export this, because I need to show you an example. Okay. Let's clear the canvas. So, okay, so let's take a look at this. Okay, let's take a look at this matrix. I'm just, for convenience, I'm taking a very simple example. So, okay, so what you can see immediately is that the matrix that I chose, this is a deliberate choice. The matrix that I chose is actually does not have a full rank, because the first row is just a linear combination of the second row. So basically, I can zero out one of the rows, okay, and the determinant turns out to be 0. And therefore, you cannot actually compute the inverse of a matrix. This matrix doesn't have an inverse because its determinant is 0, right? But however, if I follow the singular value decomposition, I can actually get 3 matrices. I'm going to skip the calculation. Let's just straight away copy the elements. This is 2, 1, minus 1, 2. Okay. 1, sorry, 1, 1. Sorry. One, 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 and minus 1. Okay. And in the middle, okay. So this is your A SVD, which after you follow that protocol of the determinant of A square minus lambda I, if you solve that, this is your U, capital U, this is your V transpose, and this is your sigma. Okay, all right. So you see how this is, I mean, how this singular matrix turns out to be a diagonal matrix. And what are the singular values, by the way? The singular values are square root of 10 and 0. Okay, so let's call this sigma 1. Let's call this sigma 2. Let's call this column as U1. Let's call this column as U2. This is as V1, and this is as V2. So, I mean, I can actually, there are 2 components here, if you look carefully. And the first component is U1, sigma 1, V1 transpose. And the second component is U2, sigma 2, and V2 transpose. Okay. So if you look at this, this is actually a low rank matrix projection. Okay. The reason being is just one value. So it's basically what you are looking at. You are looking at a transformation of rank 1. Okay. Similarly, the second component is also a transformation of rank 1. Now, since what you essentially have is that you have a spectrum of singular values, right? Sigma 1 and sigma 2. And that turns out to be, in this case, square root of 10, 0, arranged in a descending order, right? So in which direction you think the maximum information or maximum variance is disseminated? In this direction, right? Followed by this. Okay, so you think about it. I mean, if you think about it, is U1 is nothing but a combination of some input data. Okay, so it's a combination of combo of some input data, right? And V1 is a combination of some other input data, also some other input data, right? And sigma 1 is nothing but the largest singular value. So what this implies is that your first principal component is nothing but this guy. This is your first principal component, right? Followed by this guy, which is your second principal component, arranged in a descending order. Okay, so this is how singular value decomposition works. Okay, that's the essence of it. Okay, I mean, finding singular values of a matrix is not a big deal. I mean, and as I said, we will not waste our time in computing singular values or anything, right? But I hope the idea is clear. Okay, all right. So this is how we actually see how PCA is a special case of singular value decomposition. Okay, all right. But as you see here, right? I mean, this guy is real, symmetric, and positive definite because its eigenvalues are greater than or equal to 0. Okay, positive definite or positive semi-definite. Okay, all right. Okay. So let's go back to the chat box and see if we have questions. You don't have any questions. Good. Okay. So that means like we can move on to other things. And before I do that, let's export this. All right. Okay. So now that we have talked about, at least a couple of applications, right? I mean, don't get overwhelmed, okay? Because my approach is slightly different from a standard textbook approach in linear algebra, okay? So I wanted to, bring about concepts around applications. So we spoke about two applications, right? One is a principal component analysis, and the second one is the singular value decomposition, okay? And then we actually started talking about concepts in linear algebra, which are central to these applications, and therefore definitely of value to us when we talk about the pure theoretical stuff. Okay, I mean, so we established theorems and some results, not all, okay, which we require to show that why PCA works and under what conditions, why singular value decomposition works and under what conditions, and what sort of properties you would require for a particular matrix or linear transformation to satisfy. This also gives us some justification to study those properties in the first place. Okay. Otherwise, if you look at any standard textbook like Hilbert-Strang or any of the Hoffman cones, right, they actually start talking about theorems, and solve problems, theorems and solve problems, all the way up to chapter 5 or chapter 6, and then they start talking about applications. So this is something that I wanted to avoid. Okay. All right. But now, I mean, the next application or the next real, I mean, one of the classic, at least 250-year-old application which actually brought about this subject of linear algebra is that how we solve systems of linear equations. Okay, so people had a bunch of questions. Like I have a bunch of equations, okay, and all of those equations add up to 0. Okay, now I could have the number of equations exactly equal to the number of variables. I could have the number of variables greater than the number of equations, or I could have number of equations greater than the number of variables. In each one of those three cases, is there some guarantee, is there some condition which tells me that non-trivial solutions would exist? Like for example, if I write something like this, okay? If I write something like this, right? What I know straight away is that there exists a trivial solution set, which is nothing but, right? Because you have any matrix, doesn't matter. If you multiply that matrix by a 0-column vector, your output is going to become 0. But are we interested in such solutions? No. So what kind of solutions are we interested in? We are actually interested in non-trivial solutions. Okay? So in other words, what we really want to know, is there a set of vectors such that, is there a set of vectors not equal to 0 such that this will work. Okay. Now, I mean, you can find it empirically, right? But if you have thousands of equations and thousands of variables, I mean, there has to be some way to know a priori purely based on the matrix itself, right? Purely based on the matrix itself, that whether such non-trivial solutions exist or not. Okay. Man, I'm getting tired of this Sushant Singh Rajput case. Anyway. Okay. All right. So in order to do that, we need to introduce now some key concepts which are central to linear algebra. Okay. All right. And these are null space, and range, or you can call it range space. Okay. All right. These two together will actually give us a lot of information. Okay. I would also at this point of time would like to remind you that you all are familiar with this particular form, determinant of a minus lambda I equal to 0. You solve this equation, you find the eigenvalues, you find the eigenvectors, but a fundamental question is why? Why would such a representation, why does it make sense? Okay, so these are some of the questions that we would like to answer. But to begin with, now we are getting into the formal side of the subject. We need to start with some, definitions. Okay, all right. We need to start with some definitions. Okay, let me, because the internet is unreliable. Okay, so what is the first is I would want to start with a null space. Definition of a null space. Okay. Now, suppose A is a rectangular matrix. Okay, A is a rectangular matrix, M by N, induced by a linear transformation. Okay, and then the null space of A is that such set of vectors. Okay, the null space of A actually is the set of vectors X in Rn, right, such that okay, so you can see the way null space is defined has a direct connotation to systems of homogeneous equations. Whether we are able to solve such systems of homogeneous equations in such a manner that your column vectors or your solution vectors are non-trivial. Okay. Now, since we also know that everything in linear algebra has to be translated in the language of linear transformations, so let's do that now. Okay. So suppose I have a linear transformation that goes from U to V, right? Where the dimensionality U and dimensionality of V doesn't have to be the same, right? Then the null of T, by the way, the null of T is nothing. The null of T is nothing but the null of A. Okay. The null of T is the set of vectors . that T maps to 0. So in other words, we can represent null of T in the following manner. A more concise representation of null of T is this, that okay, all right. Okay, now the reason why we're talking about null space, range space, and dimensionality of the null space and dimensionality of the range space is because these are important for us to understand why their solutions to homogeneous and non-homogeneous systems exist. Okay, all right. So along the way, we will also see a fundamental theorem of linear algebra, very much like the fundamental theorem of calculus, which actually gives us a pretty good idea of why certain things work. So, I mean, at this point of time, I would like to ask you a question. Do you think that this null of T is a subspace of the vector space U? You can speak.
Yes, sir.
Yeah. Why do you think a null of T is a subspace of U?
Because firstly, there's closure under addition. Because if you add x1 and x2, then ax1 plus ax2, which is a into x1 plus x2,
right,
would also be fine.
So correct. So, but more importantly, I mean, it's a post facto verification, right? I mean, more importantly, null of T first of all is a subset of V, right? It's a subset of V with certain operations, right? It's a particular operation is T of V is equal to the 0 vector. Now, in order to show that null of T is a subspace of the vector space U, is that, I mean, you have to first convince yourself that this is a non-empty set that we are talking about, correct? It has to be a non-empty set, because if you recall, I told you that of any vector space has two subspaces always, the vector space itself and the 0. Right? So these are not the subspaces we are interested. We are actually interested in non-trivial subspaces of such vector spaces. So in order to have a non-trivial subspace, we need to have a non-trivial subset. And null of T is one such non-trivial subset. Because by definition, we are saying that we are interested to know which column vectors belong to Rn such that T of x is equal to 0. Okay. So we are not talking about an empty space, number one. And number two, there are two properties of a subspace that we have to satisfy, right? One is the closure. Now, this is very, very simple to show. I mean, because null of T is what? Null of T is the set of all vectors such that whenever you map T to any of those vectors, the mapping goes to 0. So if you choose two such vectors, x1 and x2, then T of x1 would be 0 and T of x2 would be 0, right? So how do you show that T of... So the idea is the following. I think Moitrish got it right? The idea is that if there are two vectors in null of T, right, then their sum or the additive property is also closed, right? Now, by definition, what I have is that Tx1 is 0, Tx2 is 0. Now, what I need to show is that T of x1 plus x2 is 0, right? Now, according to the properties of linear transformation, please recall that I can write T of x1 plus x2 as T of x1 plus T of x2, which is... Okay. Similarly, the scalar multiplication is also easy enough to show. So this is a subspace of the vector space U. Very, very important. Okay. All right. So this is a very important fact that null of T is a subspace of the vector space U, because we have defined the transformation from the set T goes from U to V. Similarly, The range is exactly similar as to the range of a function. So the range of a function, but so when you think of range of a function or range of the linear transformation in this case, what are we talking about? We are actually talking about taking one vector. Let me write it down again. So t goes from u to v, right? So we are talking about taking a vector here, right? Operating that vector with the linear transformation and produce something in the image space, right? So let's say there is a w which belongs to the vector space v. So by virtue of the definition of range space, it will actually contain all such w's such that your t of v will be equal to w. Okay, all right. So, and this set is called the range of the linear transformation. Once again, I mean, it is really easy to see that range of T is nothing but a subspace of. So both of these null spaces and range space, null and range, are subspaces of the respective vector spaces. Okay, so one thing we will know immediately, that the dimension, so one thing we'll know immediately, I think I can write here, that dimension of n of t, let me just represent null space t as n of t, will be less than equal to dimension of u, right? Agreed? And dimension of range of t will be less than equal to dimension of v. Okay, all right, and this gives us leverage over figuring out bases and other things. So I think probably I will first export this and then give you a small example. Okay. So let me clear the canvas. So please remember this definition of null space and range. Okay. All right. And let's look at a simple example. Okay. So let's evaluate the null space of, these following matrix. So I give you a matrix A, which is 1, -7, -3, and you can immediately see that this is not a full rank matrix. Okay, all right. So let's evaluate the null space. So what I see also immediately that this is a 2 by 2 matrix, which means what I'm talking about is that the corresponding linear transformation which induces the matrix is a linear transformation that goes from R2 to R2. Okay, so this is your U and this is your V, if you really want to relate that to the discussion that we already have. Okay, and naturally, I mean, since that there is no problem with the dimensionality, right? I mean, we can pick a column vector X, which would be a 2 by 1 column vector, right? X1 and X. Right? So we'll have X1 and X2. So by definition of null space, what do we know? By definition of null space, we know that there has to be this which will map to the 0 vector. So in other words, this T is nothing but the matrix induced by the T, right? So I have 1, minus 7, minus 3, and 21, right? X1, X2, zero, zero, right? So simple enough, right? I mean, if you look at this, I pretty much have one equation. I don't have two equations because the second row is just, 3 times, or the first row is just the, second row is just the 3 times the first row, right? So, I mean, what I really have is x1 minus 7x2 equal to 0. That's it, okay? So x1 equal to 7x2. Now, if we assign, but I really don't know, and x1, x2 are not vectors, right? These are scalars. But I really don't know what these values are. So if I just assume that x2 equal to k, let's say, right? x2 equal to k, right? Then x1 equal to 7k, and therefore the null space of this particular linear transformation will contain all vectors of the form 7k k, or in other words, k times. Okay, so all this k is a scalar. So all scalar multiples of this particular column vector will belong to this null space. Geometrically, what this implies is the following: that the null space of this particular linear transformation or the matrix is nothing but all points lying on the plane x1 minus 7x2 equal to 0. Okay, all right. So capture what we have so far is that we have a linear transformation from U to V, right? So null of T, range of T, right? Null of T is subspace of U, and range of T is subspace of V. Okay? And what is really, really important in the context of, now, typically when you have such a linear transformation, there is no guarantee that the dimension of U and dimension of V are the same. Now let's think about something that maps a vector space to another vector space, but of identical dimension. The dimension is exactly the same. Okay, so that means you are actually looking at square matrices induced by the linear transformation. Okay, so the implication in matrix algebra is nothing but, I mean, there is a fundamental theorem which says that dimension of, if I write fundamental theorem, the dimension of V, okay, is nothing but dimension of null of T plus dimension of range of T. Okay, all right. And in the context of this matrix algebra, when we are dealing with square matrices, you know that the dimension of V, because this is U and this is V, right? Okay, you know that the dimension of V is N. So in the context of matrix algebra, this implies that N is equal to null of the matrix induced by the linear transformation and range of the matrix induced by the linear transformation. And therefore, if you have a full, and this is also known as rank of the matrix, which you probably computed otherwise in your matrix algebra class before, right? This range of A is nothing but the rank, I mean the dimension, right? What I mean by, what I should have written here is the dimension of the range of A, which is nothing but the rank. So if your matrix is a full rank matrix, in other words, if your matrix is a full rank matrix which is equal to n, that would imply that your null, the dimensionality of your null space is just 0, which means the only vectors, I mean, you really, your null space does not contain anything else other than the 0 vector, which means that if you look at a system of homogeneous equations like this, the only solution that you are going to get is the 0 solution, the trivial solution. Okay, all right. So this fundamental theorem of linear algebra, by exploiting the concepts of null space and range, okay, give us very useful insights without actually getting into the painful computations as to when non-trivial solutions to systems of equations do exist or do not exist. Okay, so this will be the starting point of our discussion in the next class. Okay, all right, and in the next class also I will actually prove this rank nullity theorem. By the way, this is known as the rank nullity. Okay. I am actually uploading all the whiteboards and all the lectures, I mean video recordings and everything onto dedicated classroom folders. What I do not understand is why some of you have been asking me for access to video files when it's already available in the class folders. All right, okay, so that's it.
Sir?
Yep.
Yeah, so like you wrote that like the dimension of the range should be less than the dimension of V in one.
Less than or equal to the dimension of V, right?
Yeah, less than or equal to.
Right.
But like you can also say that like it should be less than or equal to the dimension of U, right? Because anyway, it's like the vectors in U that you finally end up with the range.
No, I can. But since the range of the linear transformation is a subspace where you are mapping it to, it makes more sense to compare the dimension of the range of T and the dimension of V. What you are saying is right, but that additional inequality will not give us any additional insight or information. Okay. So when I prove the rank nullity theorem, you will see, because there what I will do is I will create a minimum spanning list in the space U, right, and then extend it to a vector space V. Okay. All right.
Okay.
So I think it will be clarified in the next lecture. But good question. Okay. All right, guys. So we'll see you on Wednesday, regular time. Okay.